The most commonly used variants of recurrent neural networks include long short-term memories, or LSTM in short, and gated recurrent units, or GRU in short. Long short-term memories, or LSTM in short, can overcome issues in classical recurrent neural networks, such as the vanishing gradient problem. It introduces three gates, such as the input gate, the forget gate, and the output gate, as well as memory cells which are in the same shape as hidden states. We denote the input gate using the letter I, the forget gate using the letter F, and the output gate using the letter O. All the gate values at the time step t has the same shapes of size n by h, and here is the number of examples or instances, and h is the number of hidden units. Now let's have a look at each of them. The input gate it at time step t. So t here is for time step t. Sigma is a sigmoid function, which is a nonlinear activation. The gate receives contribution from the input xt at time t via the width wxi. The notation or the subscript xi means this is the width between the input x and the input gate. The input gate also receives contribution from the previous hidden state ht-1 via the width whi. The subscript hi means this is the width between the previous hidden state and the input gate. Vi here is the bias vector. Similarly, the forget gate f at time t is a function, a sigmoid function of the sum. It receives contribution from the input x at time t via the width wxf. The subscript xf means that this is the width between the input x and the forget gate f. The forget gate also receives contribution from the previous hidden state via the width whf, right? In this subscript means that this is the width between the previous hidden state and the forget gate. Bf is just the bias vector. And finally, the output gate ot at time t is a sigmoid function of the sum. It takes some contribution from the input x at time t via the width wxo. The subscript xo means that this is the width between the input x and the output gate. Also, it receives contribution from the previous hidden state h at t-1 via this width who, and the subscript ho is to mean that this is the width between the hidden state in the previous time step and the output gate. Bo here is just a bias vector. Then LSTM calculates the candidate memory cell C tilde at time t, which is very much similar as the three gates described previously, however using a time function. It takes some contribution of the input h at time t via the width w hc. The subscript hc means that this is the width between the input h and the memory cell. Also, it takes some other contribution from the previous time step h at t-1 via the width w hc, and hc means that this is the width between the previous hidden state and the memory cell. BC here is just a bias vector. The visualization helps visualize the gates and the candidate memory cell, in which we see the sigmoid nonlinearity sigma for the forget gate, the input gate, and the output gate, and the tan nonlinearity for the candidate memory cell. Then finally, the current time step memory cell C at time t combines the information of the previous time step memory cells, which is controlled by the forget gate at time t, and the current time step candidate memory cell C tilde at time t, controlled by the input gate at time t. Looking at the visualization below, we can see how it works. The current time step memory cell C at time t is a sum of some contribution of the previous time step memory cell C at t-1, controlled by the forget gate here. How much information flows through the gate from here to there is controlled by the forget gate, and it receives contribution from the candidate memory cell C tilde at time t also. And that contribution is decided by the value of the input gate. So this input gate controls the flow of information from the candidate memory cell, as we can see. The hidden state at the current time step t h. So ht basically takes the input or the flow of information from the memory cell ct, but how much, that is actually decided by the output gate ot. And this operation basically is an element by element multiplication. The range of the hidden state element is between -1 and 1 as we use the times function. The value of ht right here is between -1 and 1. Now we talked about gated recurrent units, or RGU in short. RGUs are very much like LSTMs. However, there is no output gate. Now let's have a look at the gates. The reset gate R at time t, so we denote it RT. The gate RT gets some contribution from the input HT via the width WHR. The subscript XR means that this is the width between the input and the reset gate. Also, it gets contribution from the previous time step hidden state, and this is via the width HR. The subscript HR is to mean that this is the width between the hidden state in the previous time step and the reset gate, and BR here is just the bias vector. There is the update gate ZT, Z at time t. So ZT here is equal to a sigmoid function of the sum, just like the sigmoid nonlinearity of the reset gate. So looking at the sum, we can see it takes some contribution from the input gate, just like previously. And this is via the width WHZ. HZ is to mean that this is the width between the input and the update gate. It takes contribution from the previous time step H at time t-1, and this is via the width WHZ, and HZ is to mean that this is the width between the previous hidden state in the previous time step and the update gate. And BZ here is just a bias vector similarly. The visualization on the right side help. So here we see that the reset gate gets some contribution from the input HT and also the previous hidden state HT-1. And the update gate ZT gets some contribution similarly from the previous hidden state and the input at time t. For the time step t, we calculate the candidate hidden state h tilde t via a tanh nonlinearity function. Looking at the sum, the first term shows that it takes some contribution from the input h at time t via the width WHH. The subscript XH is to mean that this is the width between the input and the candidate hidden state. It also takes contribution from this term via the width WHH. But what is this? This actually is the previous hidden state HT-1. The amount from it is controlled by RT, which is the reset gate at time t. Which we can see here. The flow information from H at time t-1 is controlled by the reset gate. This flow is then concatenated with the other flow from the input H at time t. So here we can see that the reset gate can be used to discard historical information up to the previous time step. Eventually, the hidden state H at time t can be calculated as the combination of the previous time step hidden state H at t-1 and the current time step candidate hidden state. how much it gets from the previous time step hidden state h at t minus 1. It is controlled by the value of the update get zt. So the more you get from the previous time step hidden state, the less you get from the current time step candidate hidden state, and vice versa. And again, this operation is the element by element multiplication. Looking at the visualization, you can see that h at t, the hidden state h at time t, as a sum of the contribution or the flow information from the hidden state in the previous time step. This flow information is controlled by the gate, by this gate. And also from another flow of information from the current time step candidate hidden state, and that flow is controlled by 1 minus the update gate. Usually in the architecture of a deep recurrent neural network, we can stack multiple layers on top of each other. For example, L layers in this visualization, this architecture. We can see that each hidden state is continuously passed on to the next time step of the current layer, right? And also the next layer of the current time step. The hidden state of layer L H with superscript L. In the case L is equal to 1, which is in the layer 1, hidden layer 1. And here we can see it takes contribution from the input x at time t, the hidden state from the previous time step, but in the same layer. In order to see this, we go back to the visualization, right? So this, for example, this is layer 1. At time step t, for example, t is equal to 2. It takes a contribution from the input in the same time step, and the hidden state from the previous time step, but in the same layer. And you can generalize for any L between 1 and uppercase L for the calculation of the hidden state of the hidden layer L. The output of the output layer is based on the hidden state of the hidden layer L, the uppercase L, which is the most outer layer, the most outer hidden layer. And this is via the width WHQ. Q here is the number of categories or classes, and BQ here is the bias vector. So this way we can create a deep and even very deep recurrent neural network by stacking multiple layers of gated recurrent units or long short-term memories on top of each other. Up to this point, we assume that the current time step is determined by previous time steps, so information is passed through hidden states in a forward direction. However, sometimes The current time step can be determined by later time step as well. As an example, when we write a sentence, we finish a sentence, but then want to modify the words at the beginning of the sentence. This way, the words we put in the beginning of the sentence depend on the words at the end of the sentence as well. So in bidirectional recurrent neural networks, a hidden layer that passes information in a backward direction could be added for such purposes. Looking at the architecture of a bidirectional recurrent neural network, we could see that the first layer passes information in the forward direction. The next layer on top of it passes information in the reverse direction. And we may have multiple stacks like this on top of each other. HT with the forward arrow on top of it, or we say the forward hidden state, is just the same as we saw before in the previous slide for the hidden state. We also have another, which is the backward hidden state. The two forward and backward hidden states are then concatenated to make the hidden state h at time t. And then eventually we can calculate the output layer. The output at time t, ot, is calculated based on the hidden state h at time t via the width w hq. And again, q is the number of outputs or number of categories. And bq is just a vector, a bias. And there is a note that the two directions may have different numbers of hidden units.